Chapter 1. Introduction. Information theory fundamentally addresses two primary questions in communication. The first question asks for the ultimate limit of data compression, with the answer being a quantity known as entropy. The second question seeks the maximum rate of communication over a noisy channel, which is answered by the channel capacity. The field has significant intersections with several other disciplines. Information theory is directly related to communication theory, as it defines the absolute limits for any data compression or transmission system. It connects to computer science through the concept of Kolmogorov Complexity, which defines the complexity of any piece of data as the length of the shortest computer program capable of generating it. The concept of entropy was first developed in physics and thermodynamics to describe physical disorder and formulate the second law. It has deep roots in probability and statistics, providing essential tools for analyzing sequences of random variables and testing hypotheses. There is a notable duality with economics, where the principles of optimal investment strategies and the exponential growth rate of wealth mirror concepts from information theory. Chapter 2. Entropy, Relative Entropy, and Mutual Information. This chapter introduces the core mathematical concepts that form the foundation of information theory. Entropy is a key concept that measures the average uncertainty or randomness of a random variable. It is calculated as a weighted average of the logarithm of the probabilities of all possible outcomes and represents the minimum average number of bits needed to describe an outcome. Joint entropy measures the total uncertainty of a pair or group of random variables considered together. Conditional entropy quantifies the uncertainty that remains about one random variable when the outcome of another related variable is already known. An important principle is that conditioning, on average, reduces entropy. Relative entropy, also called Kullback-Leibler distance, measures the inefficiency or distance between two probability distributions. It quantifies the penalty in coding efficiency when a code is designed for the wrong probability model. Mutual information measures the amount of information that one random variable provides about another. It is defined as the reduction in uncertainty of one variable that results from knowing the other. These quantities are interconnected through fundamental rules, such as chain rules, which decompose the entropy or information of a group of variables into a sum of simpler conditional terms. The chapter also presents crucial inequalities like the data processing inequality, which proves that processing data cannot create new information, and Fano's inequality, which establishes a lower bound on the probability of error when estimating a variable. Chapter 3. Asymptotic Equipartition Property, AEP. The asymptotic equipartition property, or AEP, is a central theorem in information theory that functions like the law of large numbers. It states that for a long sequence of IID random variables, the observed sequence is almost certain to come from a small group of sequences called the typical set. Within this typical set, every sequence is approximately equiprobable. The probability of any one of these typical sequences is a value determined by the entropy of the source. The total number of sequences in this typical set is also directly related to the entropy. This is the basis for source coding and data compression, as one only needs to create descriptions for this small set of highly probable sequences to represent the source with negligible error. The AEP thus establishes entropy as the fundamental limit for data compression. Chapter 4. Entropy rates of a stochastic process. This chapter extends the idea of entropy to handle stochastic processes, which are sequences of dependent random variables. Two key types of processes are introduced: a stationary process, whose statistical properties are constant over time, and a Markov chain, where the future is independent of the past given the present state. For these processes, the entropy rate is defined as the long-term average entropy per symbol. For a stationary process, this limit is proven to exist and is equal to the conditional entropy of the last random variable given the entire past history. In the specific case of a stationary Markov chain, this simplifies to the average entropy of the next state conditioned only on the current state. The chapter also discusses the relationship between information theory and the second law of thermodynamics. It is shown that for any Markov process, the relative entropy between two probability distributions over its states will always decrease over time, indicating that the distributions become more alike. Chapter 5. Data Compression. This chapter covers the practical aspects of data compression, focusing on methods to create codes with the shortest possible average length. An instantaneous code, also known as a prefix code, is a code where no code word is a prefix of another, which allows for immediate and unambiguous decoding. The Kraft inequality is a crucial theorem that establishes a necessary and sufficient condition on the lengths of code words for an instantaneous code to exist. It states that a specific sum involving the code word lengths must be less than or equal to 1. An optimal code is one that has the minimum possible expected length for a given source distribution. The expected length of any instantaneous code is fundamentally limited by the source's entropy. It can never be less than the entropy. Huffman coding is a celebrated and simple algorithm that constructs an optimal minimum redundancy prefix code. The algorithm works by iteratively merging the two symbols with the lowest probabilities until a single code tree is formed. Shannon-Fano-Elias coding is another constructive procedure that uses the cumulative distribution function of the source to assign code words. While not always optimal for a finite block length, it guarantees an average code word length that is very close to the entropy. Chapter 6. Gambling and Data Compression. This chapter reveals a deep and surprising duality between information theory and the mathematics of gambling and investment. The central model is a horse race, where a gambler allocates wealth across several horses with known probabilities of winning and given odds. When this gambling is repeated over many independent races, the gambler's wealth grows or shrinks exponentially. The exponent of this growth is called the doubling rate. The key insight is that the strategy that maximizes this doubling rate is proportional gambling, also known as Kelly gambling, where the fraction of wealth bet on each horse is equal to its probability of winning. The chapter establishes the following connections. A conservation theorem is established for fair races, showing that the optimal doubling rate of wealth plus the entropy of the horse race is a constant. This means that sources with low entropy, more predictable outcomes, are the most profitable for gambling. The financial value of having side information about a gamble is quantified. The increase in the optimal growth rate that results from this information is proven to be exactly equal to the mutual information between the side information and the outcome of the race. A direct link between gambling and data compression is demonstrated. A good gambler whose bets accurately reflect the probabilities of a sequence can be used to create an efficient data compression scheme for that same sequence. Chapter 7. Channel Capacity. This chapter addresses the second fundamental question of information theory. What is the ultimate rate at which information can be transmitted reliably over a noisy communication channel? This rate is the channel capacity. A discrete memoryless channel, DMC, is defined by an input alphabet, an output alphabet, and a matrix of transition probabilities, specifying the probability of receiving each output symbol for every possible input symbol. The information channel capacity, C, is a mathematical quantity defined as the maximum possible mutual information between the channel's input and output, where the maximization is taken over all possible input probability distributions. Key examples include the binary symmetric channel, BSC, where bits are flipped with a certain probability p, and the binary erasure channel, BEC, where bits are lost with probability alpha. The channel coding theorem, Shannon's second theorem, is the centerpiece of the chapter. It states that for any transmission rate r less than the capacity c, it is possible to transmit information with an arbitrarily small probability of error by using sufficiently long block codes. The proof of the theorem is based on the concepts of random coding and joint typicality. A codebook is generated randomly, and the decoder works by finding the unique code word that is jointly typical with the received noisy sequence. It is also proven that adding a feedback path from the receiver back to the sender does not increase the capacity of a discrete memoryless channel. Chapter 8. Differential Entropy. This chapter extends the concepts of entropy and mutual information from discrete random variables to continuous random variables. Differential entropy is defined for a continuous random variable using an integral that is analogous to the summation used for discrete entropy. A key difference is that differential entropy can be negative. The asymptotic equipartition property also applies to continuous variables. For a long sequence of such variables, there exists a typical set that contains almost all the probability. The differential entropy is related to the logarithm of the geometric volume of this typical set. The relationship to discrete entropy is clarified by considering a finely quantized version of a continuous variable. The entropy of the quantized variable is approximately the differential entropy plus a term related to the size of the quantization intervals. A crucial result of this chapter is that the Gaussian or normal distribution possesses the maximum differential entropy among all distributions that have the same variance. While differential entropy has unique properties, the concept of relative entropy and mutual information for continuous variables are direct extensions of their discrete counterparts and retain their fundamental properties. Chapter 9. Gaussian Channel. This chapter analyzes the additive white Gaussian noise channel, which is a fundamental model for many real-world communication systems. In this channel, the received signal is the sum of the transmitted signal and a noise variable with a Gaussian distribution. The capacity of the AWGN channel is finite only if the input signal's power is constrained. For a given average power constraint P and a noise power N, the channel capacity is precisely given by a formula involving the logarithm of 1 plus the signal-to-noise ratio. For band-limited channels, which are constrained to a specific frequency bandwidth W, the continuous time channel can be modeled as 2W independent discrete time Gaussian channels per second, according to the Nyquist-Shannon sampling theorem. The concept of water filling is introduced to determine the optimal power allocation across several parallel Gaussian channels. To maximize the total capacity under a total power constraint, more power should be allocated to the channels with less noise. The chapter also confirms that for the standard memoryless AWGN channel, adding a feedback mechanism does not increase the channel's capacity. Chapter 10. Rate distortion theory. This chapter explores the theory of lossy compression, which deals with representing data when perfect reconstruction is not required and some level of error, or distortion, is permissible. It addresses the fundamental trade-off between the compression rate, R, and the resulting distortion, D. A distortion measure is a function that quantifies the penalty for representing an original symbol with a different reconstructed symbol. Common examples are the squared error distortion and the Hamming distortion. The rate distortion function, RD, defines the minimum number of bits per symbol required to represent a source while ensuring that the average distortion does not exceed a specified level, D. The rate distortion theorem proves that this theoretical information-based function is the operational limit. It is possible to design codes that achieve any rate distortion pair, RD, as long as the rate R is greater than the value given by the function, RD. Key examples are calculated for the Bernoulli source with error probability as the distortion measure and for the Gaussian source with squared error distortion. The theory also demonstrates the power of vector quantization, showing that encoding long blocks of symbols together is more efficient than encoding each symbol individually. Chapter 11: Information Theory and Statistics. This chapter delves into the significant connections between the concepts of information theory and the field of statistics. The method of types is a powerful combinatorial framework for analyzing the properties of long sequences. The type of a sequence is simply its observed empirical probability distribution. Sanov's theorem, a cornerstone of large deviation theory, uses the method of types to precisely calculate the probability of rare events. It states that the probability that an empirical distribution falls into an unusual set of distributions decays exponentially, with the exponent given by the minimum relative entropy between that set and the true underlying distribution. The chapter applies these ideas to hypothesis testing. The Chernoff-Stein lemma provides the best possible exponent for the probability of error when deciding between two competing hypotheses based on a sequence of data. Finally, the chapter introduces Fisher information, a measure of the amount of information that an observable random variable carries about an unknown parameter of its distribution. The Kramer-Rao inequality provides a fundamental lower bound on the variance of any unbiased estimator for this parameter. Chapter 12: Maximum Entropy. This chapter focuses on the principle of maximum entropy, a foundational concept for statistical inference. The principle states that when selecting a probability distribution from a class of distributions that are all consistent with certain known constraints, one should choose the distribution that has the highest entropy. This choice is justified because the maximum entropy distribution is the one that is most random or makes the fewest assumptions beyond the given constraints. The distribution that maximizes the entropy subject to moment constraints is always of an exponential form. Given a fixed variance, the normal Gaussian distribution has the maximum differential entropy. Given a fixed mean for a non-negative variable, the exponential distribution has the maximum entropy. The principle has a significant application in spectrum estimation. The maximum entropy method estimates the full power spectrum from a limited number of autocorrelation values by finding the spectrum corresponding to the most random stochastic process consistent with the known values. Chapter 13: Universal Source Coding. This chapter addresses the practical problem of data compression when the statistical properties of the source are not known in advance. It introduces universal codes, which are single coding schemes designed to perform well across an entire class of potential sources. The concept of minimax redundancy is introduced to analyze the performance of such codes. The goal is to find a code whose worst-case performance penalty is minimized. Arithmetic coding is presented as a practical, online method for implementing universal coding schemes. It maps an entire sequence of symbols to a fractional number and can adapt its encoding based on the statistics of the data as it is being processed. The chapter culminates with a discussion of the Lempel-Ziv algorithms, a famous family of universal compression schemes. These algorithms work by adaptively building a dictionary of phrases encountered in the input data. LZ algorithms are provably optimal in the limit. As the sequence length goes to infinity, their compression ratio converges to the entropy rate of the source. Chapter 14: Kolmogorov Complexity. This chapter introduces a fundamentally different approach to complexity, shifting from the probabilistic framework of Shannon entropy to an algorithmic one. The Kolmogorov complexity of an object is defined as the length of the shortest possible computer program that can generate that object and then halt. This provides an ultimate, intrinsic measure of the descriptive complexity of an individual object. A key concept is universality. The complexity value is fundamentally machine-independent, varying only by a constant between different universal computers. Most strings are complex and incompressible, meaning their Kolmogorov complexity is nearly equal to their length. Such strings are deemed algorithmically random. A profound link to Shannon's work is established. The expected Kolmogorov complexity of a sequence generated by a random source is approximately equal to its Shannon entropy. The concept of universal probability is also introduced, where the probability of a string is defined by the likelihood that a random program will produce it. Simpler strings have a higher universal probability. This framework provides a formal basis for philosophical principles like Occam's razor and the minimum description length MDL principle. Chapter 15: Network Information Theory. This chapter explores the complexities of communication in networks that involve multiple users, a field known as network information theory. This introduces new challenges such as interference and cooperation. The Multiple Access Channel, MAC, involves several transmitters sending independent messages to a single receiver. The capacity region is a multidimensional volume defined by constraints on individual and sum rates. Slepian-Wolf coding, or distributed source coding, is the corresponding data compression problem. It shows that if two correlated sources are encoded separately, they can still be decoded jointly with the same total rate as if they had been encoded together, namely their joint entropy. The broadcast channel, BC, features one sender transmitting information to multiple receivers. For the special case of a degraded channel, the capacity is known and is achieved through a technique called superposition coding. The relay channel involves intermediate nodes that help facilitate communication between a source and a destination. Its capacity is also known only in special cases. A key takeaway is that the source-channel separation theorem, a cornerstone of single-user theory, does not generally hold in network scenarios. Chapter 16: Information Theory and Portfolio Theory. This chapter provides a deeper exploration of the powerful analogy between information theory and the theory of financial investment, focusing specifically on the stock market. The chapter contrasts the traditional mean variance approach to portfolio management with a strategy based on maximizing the long-term exponential growth rate of wealth. The portfolio that achieves this is known as the log-optimal portfolio. The log-optimal portfolio is also demonstrated to be competitively optimal in the short term. In a single-period investment game, this strategy maximizes the probability of having more wealth than an opponent. A major contribution of the chapter is the introduction of the universal portfolio. This is a practical, causal investment strategy that does not require any statistical knowledge of the market. The remarkable result is that this universal strategy achieves the same asymptotic exponential growth rate as the best constant rebalanced portfolio chosen in hindsight. The chapter concludes by using the insights from portfolio theory to provide a novel sandwich proof of the asymptotic equipartition property for general stationary ergodic processes. Chapter 17: Inequalities in Information Theory. This chapter serves as a synthesis and summary of the fundamental mathematical inequalities that form the backbone of information theory, while also introducing several new ones. The chapter begins by reviewing the core inequalities that arise from the property of convexity, such as Jensen's inequality and the log-sum inequality. It then extends this review to the realm of differential entropy for continuous variables, using information theoretic proofs to derive classic mathematical results like Hadamard's inequality for matrix determinants. New inequalities are presented concerning the entropy rates of randomly chosen subsets of random variables. A deeper connection is forged between Shannon entropy and Fisher information. The chapter features De Bruyn's identity, which relates the two concepts through differentiation. This connection is used to outline a unified proof for two major inequalities, the entropy power inequality, EPI, which bounds the entropy of a sum of independent random variables, and the Brun-Minkowski inequality, a fundamental result in geometry concerning the volume of the sum of two sets.
That's all for this episode of Geek Capsule. We hope it gave you a fresh perspective on the world of technology. We'd love to hear your thoughts, so feel free to leave a comment or share your feedback. If you enjoyed the show, don't forget to subscribe and join us next time for another essential read. Until then, keep your curiosity sparked and your mind open.